So hello everyone, I'm TELEM AVIDOR, the ESR number 1 of the project under the work package 4, wind resource assessment. And I will present to you today the topic of the implementation of the advection time to improve the correlation between space-distributed meteorological dataset. And my supervisor is Sandrine Aubrin from Central Nantes. So I will first present the study case where I get the data. So it's South Brittany in France. So we can see here, Nantes is here, and the region is really interesting for wind turbine, as it's quite windy. And the first European commercial floating project should appear here in 2028. It will be at least 250 megawatt. And to know a bit more the wind in the region, the French state with Météo France installed 2 floating LiDAR in this area. And more generally, when we go offshore, we have a significant distance between our point of interest. We can see here our LiDAR are separated by more than 20 kilometers. If you have other meteorological stations onshore, they will be 70 kilometers apart. The wind farm will be also a bit further. So it asks the question, when you compare some data set, when you do extrapolation, how to manage this spatial distance, and that's the context of this study. The 2 LiDARs, they are from Leosphere WindCube version 2. I will call them, to be more generic in the study, the north LiDAR, I will call it reference, and the LiDAR, the south one, I will call it target when I will speak about the results. They both measure the 10-minute average wind speed and wind direction at different height, from 40 to 200 meters every 20 meters. And I will use the data at 100 meters for this study. And they both measure the data for 1 year. So I have a concurrent data for both stations during 1 year. If we take a quick look at the wind rose measured by the LiDAR, we can see that in this region, the wind is mainly coming from the west, and a bit also from a dominant wind also from the northeast. So the advection time, I define it as how much time for the wind to go from the target station to the reference station. So let's do a little exercise to estimate the advection time on a typical wind condition. Let's say that so here the distance between both stations is 20 kilometers. The wind speed is going from the target, so the wind is going from the target to the reference at 7 meters per second. So if we do a quick order of magnitude, we can say that the traveling time, so advection time, is the distance over the speed. Here, it's 50 minutes. So if you have 10-minute data set, 50 minutes represents 5 time steps. So it's a challenge because if the time lag, the traveling time is 5 time steps, it means that if you want to compare the wind speed at the target at the time t to the wind speed at the reference, you should not compare it at the same time, but you should take into account this lag. And it will be better to compare the wind speed at the target at the time t with the wind speed at the reference at the time t plus the advection time, because to take into account. So the idea is that a correction of the wind speed at the reference is necessary before comparing it to the wind speed at the target. And all the point of this presentation is to find this lag for each time. The methodology, so I assume that by doing this correction, my correlation between the both wind speed will be better. But to measure how good is the correlation between the station, I will use the Pearson coefficient. So you have the definition here. I think all of you know what is it. It's, for example, when you do a linear regression analysis and you have this coefficient here, that's the Pearson coefficient usually. So the closer it's to 1, it means that your 2 data sets that you are comparing are quite well correlated. And if it goes down to 0, it means that they are totally independent. I will use, so how to estimate this time lag? I will use two methods. A first method that I call theoretical or variable. So I will estimate myself the time lag based on the speed and the direction. While I will use a second method, that I call it empirical or constant. I will just select the time lag that maximizes the correlation coefficient, but then it will only be one unique value, and I will do it by sector of direction. So the first method is more ambitious because I try myself because it's variable for each time step based on the current speed and current direction. So based on physics value, I try to estimate the time lag. While the second one, it's only one time lag by sector of direction, so much less flexible. But the first method is less robust because if my estimation of the time lag is totally wrong, then I will just decrease the correlation coefficient. And the second method is more robust because it will automatically increase the correlation coefficient as the time lag has been chosen to maximize it. So let's go a bit more in detail. On the first method, I say that for each time step, that the time lag is equal to the streamwise distance over the wind speed. And the streamwise distance here is if we say that the wind is going in this direction and that this direction is the direction of between the two stations. So the streamwise distance is the distance between the two stations projected with this angle alpha. So it's dRt cos alpha over the wind speed. And alpha is the difference between the direction here and the wind direction. So you can ask which wind speed and which wind direction I'm talking about here. Is it the one that measured at the target or the one at reference, an average? I did a filter of the target data to avoid, so I took the data at the target, but 1 hour average, because I didn't want to have too much fluctuation. I wanted to represent the traveling time. So you can see in black the advection speed that I use. It's like the wind speed at the target, which is 10 minutes initially, but average in 1 hour. I'm still on the first method. So I'm keeping this equation to estimate the time lag, but I'm not using it for low speed for two reasons. First, I think that the coherence of the wind structures and the eddies is not high enough on the low wind speed to say that they will be on the same state while traveling. So the correlation there will be no correlation in low wind speed with the high distance between the two stations. And secondly, because anyway, the low wind speed are not interesting for the wind energy in a wind turbine. So what I do is that below 5 meters per second. Here, if we look at this figure here, so I plot the time lag according to the wind speed. So it's inversely proportional. So we can see that if I keep the equation like this, on low wind speed, I will just say, oh, the time lag is huge, and it's not true. So I just don't delay the equation below 5 meters per second and say that there is no time lag. We could have done other things, but it was working well. So I keep it like this. The second method. So on the second method, I divide my data into 12 sectors of direction of 30 degrees, and I will compute the time lag for each sector of direction. So I don't take into account the speed here. So for each sector of direction, I select all the data from this sector. I compute the correlation coefficient between both stations, So it gives this figure. So for each direction sector, we have one correlation coefficient. Then I apply a correction, time lag correction by using different time lag, and I find the time lag that maximizes the correlation coefficient. So if we take, for an example, with a bin 12 here, we can see that if we don't do anything, so 0 time shift, we have 0.86, a bit less initially as a correlation coefficient. And we apply different correction in the time lag, and we can see that we have a maximum at less 30 minutes here. It means that in average in this sector, in this sector of direction, the wind take 30 minutes to go from the reference to the target. So here it's less 30 minutes because I take it from the target. And I do that for every sector of direction. And you can see that, so here in blue is the correlation coefficient that I get with this method. And we can see that it increases the initial correlation coefficient more or less according to the sector of direction. Now I will compare the results for the two methods. So here I plot the time lag obtained with the method 1, where I estimate myself the time lag. So I don't have a unique time lag by sector of direction. I have a time lag for each time step. So I represent the time lag with a box plot. So the box plot here, you have a big example here. This is the mean line. This is the median line. This is the first quarter quantile, then the third one. So and then you have the lowest data in the quantile 1, less 1.5, the difference about the quantile 3 and quantile 1, so 25% and 75% quantile. So it's the box plot given by Python when you have a bunch of data and the flyers outside the range. So we can see that in general, our time lag are between a bit more than less 60 minutes and a bit more than 60 minutes. It's because we restrain the wind speed to 5 meters per second. So we have a limited value for the traveling time. We can see that we have a cosinus trend because it had been built like this, so it's normal. And we have a maximum traveling time for the bin 6 because it's exactly in the direction of the target to the reference. And we have a minimum for the bin 12. Now, if I put on it the time lag that I found with the constant method, we can see that globally the trend is a bit the same, but they are not overlapping. And we can see globally that the time lag found with the that I found with the constant method in absolute value is less than with the one I compute myself with the first method. Let's see then the correlation coefficient, how much it improves with both method. So in the black line here is the correlation coefficient that we have initially, so without doing any correction. In blue is the one we saw before with a constant method, and in green here is a variable method. So we can see that here, if we take the number 12, both methods increase the correlation coefficient globally, but the same amount. But in general, the constant method is always better than the variable method, which is a bit disappointed, but it's a result. And we can see that the improvement is quite significant for when the wind is coming from the north here, so the bin 12, 11, and bin number 1. It's working well, but on the other direction, so for example, if we take the reverse direction on the south, the constant method is improving really slightly the correlation coefficient, and the variable method I did, it doesn't work. It's decreasing the correlation coefficient, so it should not be used. We can also note that it's working well when the correlation coefficients are initially the lowest. But globally, I didn't find any explanation on why it's working better from the north than from the south. If we now some conclusion, I can say that the variable method is not better than the constant method so far. And the constant method shows some improvement, especially when dependent on the sector of direction. And it's really easy to implement, so it can be done super easily. In the future, on the future work, we can do, if we speak about the variable method, I can do a lot of sensitivity analysis on all the different parameters that are used to compute the time lag, and also especially more study case to have more pair of data sets to try both methods. So thank you for listening.
Thank you, TELEM, for your presentation. So are there any questions? Yes.
TELEM, I'm just wondering what your rationale was between like the 12 sectors and directional sectors. Is there any reason why you picked 12, not more, not less? Do you think you'd had more accuracy if you had like a more like sort of smaller bands with your sectors, or do you have an answer to that?
I took 12 sectors because it's usually what is used in the industry when they want to correlate some data set. They take 12 sectors of 30 degrees, and it's really used in the industry, especially in the what they call the MCP method, so measure, correlate, predict. They will because the correlation you can have on between both stations can be totally different according if you take the wind that is coming from for example from the earth, from the coast, or from the ocean, or from the north. So you can have different transfer function between the two, and usually in the industry they take 12 sectors. It's why I keep it like this. But I could, and it's also having a compromise between keeping a number of data which is still high enough to have not too much bias on your correlation coefficient, but still be enough refined to have a common properties, to have a direction that is not fluctuating too much.
Great, thanks.
Thanks for clarity and explaining all your different methods. I would like to know actually why are you doing this kind of models? Why are you developing that? Is that in the end you use one station to estimate the wind speed pretty much everywhere on the sea, or what's the, let's say, the application of this work for offshore development? Or
yeah, it's quite correlated to the question before. It's for example in the MCP method when you want to establish a transfer function between the two. So imagine, for example, you have so because it's really expensive to install floating LiDAR on the offshore, so usually they will do it for 1 year, and they will have only 1 year of data, and they will you will have, for example, a station here on the coast that maybe is running for 20 years, and if you succeed to correlate well these two stations, then you can use the data that you have here to, and imagine, for example, you want to install a wind farm here. You use this data to estimate the energy that you will produce, but you have only 1 year of data, so it's not, you have a lot of uncertainties. But if you succeed to correlate it with the 20 years you have here, you can use 20 years of data to have another source of information, and then reduce the uncertainties on your production.
Yeah, okay, very clear. May I ask quickly another one? I'm also surprised that the sector 2 is actually working quite well, right? The correlation coefficient is around 0.9. But if you look at the wind that is coming from direction 2, on the top, it's somehow from the open sea. And on the right, it will hit the island first. And still, there is quite a strong correlation. Is it? something that you expected, or?
No, not really. It's also why I say I don't really have explanation on why what I did is working better from north despite south, because south there is no influence of any topography. For the island here, it's mainly I didn't look too much on the advection time result, because anyway, when it's coming perpendicularly, you don't expect traveling time. But indeed, the fact that the correlation coefficients are quite high when the wind is going through the island here, I will say it's because of the distance. Maybe if it was closer, the island would have more influence. But here, maybe the wind has time to recover from the island. Yeah. But we can see, yeah.
Okay, nice. Thanks.
So there is also one question online regarding that, by asking whether there can be an influence also of the wind rose distribution and the wind speed distribution that you have in each wind direction beam, that maybe that can also generate a bias, because you do not have the same wind speed distribution in all directions.
Yeah, it's something. We look at it to find some explanation, and the wind speed distribution was not a reason for that. And we try also here for clarity. I present the result of the constant method with only beam of direction, but I also did it by beam of speed and beam of direction, and the results were surprisingly not that much better. It was a bit better, but not that much better. So the influence of the speed was not clear, but it also maybe explains why the variable method is not working that well. Is that there is some limitation of at least with 10-minute dataset on how much we can this advection is true. So yeah, the wind speed, I don't know what was the question exactly, but
you will read it.
If he can explain, it doesn't explain the result, at least that I have.
Okay. Another questions? Yes.
Yes. Thank you. I think there is a hidden hypothesis that is that the integral length scale of turbulence is smaller than the distance between your 2 points.
Yeah.
Because otherwise you may have spurious correlations that are not from the mean advected flow. Did you check if this is the case for all your data set, or?
I didn't look. It's why I delayed the data, and if I ignore the data below 5 meters per second, for example. I try to different wind speed because I assume that below this the integral length scale will be lower for this wind speed, and so I try different wind speeds that I will ignore and see how much it affects the result. And I saw that 5 meters per second was a good compromise, but I didn't check specifically the value of the integral length scale compared to my the distance, the initial distance.
Maybe a remark or question, I don't know exactly, but you tell that the difference is, yeah, it's a question. Between north and south, there is a difference. My question is, did you also look at the wind shear?
Yeah.
Did you look at that? And is there? That's the second question. Is also are the waves also? Is the wave height also measured in this together? Is it, or is there no wave information?
I think you can find wave height maybe with different models. So for the first question, the wind shear, I try to look at it because it was also we had this question also. For us, it was really hope to see that it will be an explanation. So what we did is that we did the same simulation, but with by sorting by stability or by wind shear value. So we say we do it only with a perfect, with a standard, with a wind shear between this range, and then we do the same with the wind shear between this range. And it didn't really, it was not clear. That was the reason.
But you, this LiDAR measures at different heights, so you can also estimate from the measurements, I think.
Yeah, it's what we did.
Okay.
We estimate the wind shear based on the LiDAR data, and then we did the simulation by keeping, for example, only the data that has this specific wind shear. And we can see then if the result changed or not. And it was not clear that the wind shear was the reason why. And the second question was the wave.
No, yeah, that's if it was clear, then I would say look at also at the wave height, because then there might be a difference in wave height that because waves cause this.
Here is the data at 100 meter high, and so I don't think it's really that much influenced by the wave. And I also tried with 200 meter, and it was similar results.
No, but in general, wind shear is dependent on the wave height.
Ah, for the wind shear value.
Yeah.
Oh, yeah.
So it's like I think a Charnock relation. Then it has with higher wind speeds, or then you have higher waves, and then the roughness of your surface is higher, and then you get a different wind shear.
Yeah.
So that's why I asked this question about the waves. But if you didn't find any difference in the effect of the wind shear, then it's not useful to look at the waves. I
didn't look specifically on the link wind shear wave. It's just
it's only of interest if you say probably it is it's caused, and this difference in north south is caused by I don't know where the waves come from north or from south, and then if there's a difference, then and it's caused by this wind shear.
Yeah, would be nice.
You can look at the waves, but if there's no difference, say, don't look at it.
Maybe you can mention also that you are using the AROM data, so reanalysis data from this region to try to...
I have the AROM data, but the issue is that I cannot use them to do the same kind of study because it's one hour time step. And if I estimate the time lag to be between 0 and 1 hour, the time shift that I will have to do in my data will be 0 or 1, and I need to work with 10-minute data in this study case to see the influence of the time shift. While the AROM data that I had are 1 hour. So.
But the space correlation was more or less homogeneous around the site, except close to the island, I think.
Yeah, the island has an influence, but maybe it has an influence around here, but not till here. Yeah.
A last question for the audience? No? Okay, so let's thank the two speakers of this last session.